Today we're going to look at a lesson unit 3. This is going to work with polynomial and rational inequalities. This is going to be in chapter 5, section 5 as well. So the first part of this lesson, we're going to kind of go back a step and just look at solving a linear inequality. In other words, a degree 1 inequality. The strategy we're going to use is a number line. So some things that to stay consistent is we're going to set the inequality to 0. So one side has to be set to 0. The next thing we're going to do is we're going to determine a 0 or an x-intercept. Again, we can do this algebraically on paper, but we also can use our graphing tools to find zeros and x-intercepts as well. We can mark the zeros on the number line. So once we do that, another thing we have to pick up on is the 0 included or not included? If it's greater than 0, remember that's an open interval, so those zeros will not be included. If it's greater than or equal to 0, the interval is going to be closed, so those zeros are going to be included. Also, the interval we're looking for will have to be positive, because to be greater than 0 means you have to have something that's positive. Positive numbers are greater than 0. So when we're looking for answers, we're also looking for these positive values. Less than 0, remember that's an open interval, so the 0 is not going to be included. If it's less than or equal to 0, that's a closed interval, so the 0 will be included. Again, the interval will need to be negative because less than 0 means you're looking for negative values, so that kind of gives us some clues of what we are looking for. So when we use this number line, what we're going to do is test each side of the 0. So the zeros are going to create intervals on the number line, and we're going to test each side of that. So the interval will be determined by the inequality symbol. It's like I said, if it's greater than or greater than or equal to, we're looking for a positive. If it's less than or less than or equal to, then we're looking for where the interval is negative. So let's look at this inequality here. Solve each inequality. So I have 2x is greater than or equal to 18. Again, using our strategy that I'm suggesting is we set this to 0, so we're going to lose 18 on both sides. So this becomes 2x minus 18 is greater than or equal to 0. So we start out there. Now, to find the zeros, what I can do is I can set 2x minus 18 equal to 0, and I can solve for x to find a 0. So I can move the 18 back over. 2x is going to equal 18. Divide each side by 2, and x is going to equal 9. So on our number line, we're going to mark the 9. Now, notice how we have a greater than or equal to symbol. Greater than or equal to means the 9 is included in our interval. So we use a solid dot here. The 9 is included. And greater than also means we're looking for positive. So this means we're also looking for positive values. So to test this interval, we can test left of 9 to start with. And over here somewhere, notice that 0 is left of 9. So what I can do is put 9 into this problem and see if it makes it a positive value or a negative value. So if I do 2 times 0 minus 18, that's going to be 0 minus 18. And that's going to end up being a negative 18. So left of 9, this interval over here is going to be negative. Now, if I pick something right of 9, and let's pick an easy number right of 9, I think 10 would be an easy value to pick right of 9. So if I pick 10, that's going to be 2 times 10 minus 18. That's going to be 20 minus 18. That's going to be a positive 2. So when I'm right of 9, I'm getting a positive value. So what we pick up on then in this problem is if I am left of 9, it's negative. If I'm right of 9, it's positive. So as we said, we are looking for this positive value. So what we do is we shade to the right of 9 as well. That's going to be where our solution exists. So our answer is going to be using an interval notation. Our solution to this problem will be then, since the 9 is included, I need to use a bracket since we're going to use interval notation, I think, a lot in this section. They kind of go back and forth. So we're going to use a bracket and then 9, and then we go to infinity. Infinity is always an open bound. So that would be our solution using interval notation. So if I look at this example here, I have 5x is less than 0. Again, to solve an inequality, a strategy we can impose is set this to 0 to start with. So 5x minus 18 is going to be less than 0. So from there, I need to actually find the 0 or the x-intercept. So what I can do is set 5x minus 18 equal to 0 and actually solve for x to find the x-intercept or 0. So x is going to 5x is going to equal this 18. And if I divide both sides by 5, I get this 18 divided by 5. So I have 18/5. So if we want, we can leave it as that. But as far as like understanding it better, we may want to look what that looks like as a decimal. So if I quit this graph, I hit 18 divided by 5, we see that we get 3.6. So 3.6 is what we're seeing there. So now you have to pay attention to, in my lab math, whether or not they'll accept a decimal or not. If not, we have to leave it back as 18/5. So up here on my graph, I'm going to go ahead and just leave it as a fraction, knowing though that that's the same thing as 3.6. Notice that since this is less than 0, this is an open interval at this spot. We do not include the 0. Now, since it's less than 0, what we're looking for is we want this left side to be negative. So again, if we test an interval, something left of 3.6, again, 0 would be an easy value to pick left of 0 or left of 18/5 or 3.6. So if I put 0 into the problem, I have 5 times 0 minus 18. 0 minus 18, again, is going to be negative 18. So that is going to end up being a negative interval over here. That's what we're looking for. But let's just double check to see what the right-hand side looks like. So something right at 3.6 would be like 4. 4 would be right of that. So if I type in 5 times 4 minus 18 is less than 0, or really don't need that part. I'm just looking for a negative value. So, or a positive value for that matter. So 20 minus 18 would be 2. So that would be a positive value. So right of 18 would be positive. And since we were looking for negative, this tells us to kind of shade to the left. That's where it's going to be negative. So anything left of 3.6 should create a negative value. And like I said, all the way out to, remember, this over here is negative infinity. And way over here is positive infinity. So our interval that we're looking for is the negative part. So using interval notation, we're going to see our answer is going to be negative infinity to this 18/5 if I'm using fractions. If they don't give you, if they don't tell you anything about that, then you can also probably use a decimal there. But just if it says integers or fractions, then you cannot use a decimal. So if we look at this example here, I have negative 6x is greater than 12. Again, to set this to 0, we have negative 6x is minus 12 is going to be greater than 0. So again, to understand the solution, we're going to find the actual x-intercept or 0. So we're going to set negative 6x minus 12 equal to 0. We're going to solve for x, and we're going to get negative 6x is equal to 12. And then we divide each side by negative 6, and we get x equals negative 2. So negative 2 would be my 0. So on my number line, I'm going to mark that critical point, that 0, or x-intercept, if you will. So now if you look, since it's greater than, that means we have an open bound. So that means we do not include the 0 in our solution. And greater than 0 means this has got to actually be a positive over here. So I'm testing my interval left of -2, -3 would be left of -2. So if I substitute -3 in, -6 times -3 minus 12, if I do that math, that's going to be 18 minus 12, which is going to be a 6. So it's going to create a positive value. So over here is going to be positive. And if I choose something right of 0, or sorry, right of -2, 0 could be a good choice again, because that makes the math a little bit easier for me. Again, you can choose anything you want. So -6, put a 0 in, minus 12, that's going to be 0 minus 12, and that is going to be a -12. So over here, it's going to be negative. But since we're looking for something greater than 0, we're looking for a positive, we'd be looking for something left of -2. So again, our interval is going to be over here. In this situation, again, this is going to be negative infinity over here, and this is going to be infinity on this side. So our solution, again, since we're looking for positive values, is going to be from negative infinity to -2, and we do not include the -2 in our solution, so it's an open bound again. So that's how we can kind of solve these inequalities. We also could be using the Ti84 calculator. So again, above the x-axis is positive and below the x-axis is negative. So for instance, on this one right here, if I graphed y equals -6 minus 12, if I actually graph that function, -6x minus 12. So if I go here and click on my decimals and clear that off and type in -6x minus 12, if I hit the graph button, notice that the x-intercept is -2, and notice that the graph is above the x-axis left of -2. Notice that the graph is below the x-axis right of -2. So that also indicates that situation that this is positive interval, this is negative interval, so you'd be left at -2 on the number line. So you can also just graph the function, you can see the x-intercept, and then you can kind of go from there. So the next thing we're going to work into is we're going to solve a quadratic inequality, degree 2 inequalities. So again, we're going to set one side of the inequality to 0, and then we're going to find the zeros where x-intercepts by factoring. We're going to mark those zeros on the number line. So remember, greater than 0 would be open, greater than equal to 0 would be closed, and that means we're looking for positive values. If we have a less than 0, again, that's open, less than or equal to 0 is closed, but less than means we're looking for negative values. Also, if we're using graphing behavior, remember with quadratics, if A is positive, the graph is going to open up. So that helps us with some behavior if we're looking at the graphing calculator. Remember, if A is negative, this graph is going to open down. So remember, where the behavior is above the number line, the interval is positive. Where the behavior is below the number line, the interval is negative. So again, we're going to write the interval using either set builder notation or interval notation. And I believe in this lesson, it's interval notation. So if we want to solve this inequality, notice how it's right set to 0. But if I want to find the x-intercepts or zeros, what I can do is set x squared minus 6x plus 8 equal to 0, and I can solve that. Since the quadratic term is x squared, we know right off the bat, the first two pieces have to be x. The catch is now, what goes in these last two positions are the factors of 8. Remember, the factors of 8 are 1 and 8, 2 and 4, and that would be it. So, but the catch is these factors of 8 have to add up to give you the coefficient of the linear term. So I'm needing this -6 as well. So it's got to pass both tests. So the factors of 8 that have to add up to give me this -6. So right now, I'm really not seeing anything going on here, but this 2 and 4 looks like it can give me this 6, but it doesn't give me a -6. But if I do make them both negative, and we do know that a negative times negative is actually a positive, so that does give me a +8, and that does add up to give me a -6. So this gives me then my -2 here and my -4 here is equal to 0. So what we do now is we set each one of these factors equal to 0 using the multiplication property of 0. To get 0, one of these factors has to be 0. So we're asking ourselves, well, what makes x minus 2 equal to 0? Well, that would be 2. If I look at this factor x minus 4, what makes it 0? X would be 4. So if you put 2 or 4 into this problem, it's going to turn the whole thing into 0, and that's what we're looking for. And again, that's why we call 2 and 4 zeros, is because it makes the function 0. So now if we graph these on the number line, we have the 2 would be over here on the left, and the 4 would be on the right. So make sure you get the smallest number on the left and the bigger number on the right. So notice how it's greater than or equal to 0. That means these zeros are actually included in the solution. So we close those in. They're going to be included. Now, greater than 0 also means we're looking for a positive value. So this left side has to be positive. Notice how, since a is positive here, we know that this parabola has to open up. So it's going to have to pass through these x-intercepts here, and it's going to have to open up. So it's got to be up over here. It's got to come down, and it's got to cross over here, and it's going to go up again. So I can use the behavior of a quadratic equation to kind of pick up on where it's positive. You also can just test the intervals if you want to. So if you're like, I'm not sure about this quadratic stuff, if you just test the 3 intervals, if I test left of 2, a number left of 2 would be 0. So if I put 0 into my problem, so I have 0 minus 2 times 0 minus 4, that's going to give me a -2 times a -4, and that does give me a +8. And that kind of verifies that since the graph is above the x-axis, that's positive. So a number between 2 and 4, not many. 3 is a choice, though, we could choose. So if I choose 3 minus 2, so 3 would be located here. 3 minus 2, 3 minus 4. That's going to be 1 times -1. Well, that's going to be a -1. So it's going to be negative in this interval. And that's what's happening to my graph. It's below the x-axis or below my number line. And if we choose something right of 4, say 5, it should give us something above the graph as well. So if I go 5 minus 2 times 5 minus 4, we get 3 times 1, which would be 3. So notice that it is positive here, it's negative here, and it's positive here. So we only want where it's positive, so it would be these 2 intervals. So our answer to this problem would be then, I'm just going to come back over here and write it. It's going to be, again, remember way over here is -infinity. Way over here is +infinity. So again, if we're doing interval notation, we go from left to right. So -infinity to 2. And the 2 is included in the solution. So we use a bracket. In union with, since there's 2 actual union, this over here is actually positive as well. So we're also going to pick 4 to infinity. So 4 to infinity would be the other interval that makes this true. So again, that would be all the solutions that solve this inequality. So if I look at this quadratic inequality, again, it's already set to 0, so we don't have to do anything there. But we now want to find the zeros. So I can go x squared plus x minus 12 is equal to 0. Again, to factor this, since that's x squared, we know that's got to be an x and an x. But the catch is we have to figure out what are the factors of a -12 that add up to give me the coefficient of the linear term. And the coefficient of the linear term would be like that 1x there. So I need a 1 there for that. So the factors of 12, I'm seeing like a 1 and a 12, a 2 and a 6, a 3 and a 4, and 4 and 3. That's repeating now. So I just have those 3 pairs. The 3 and 4 looks like the best choice, but as is, it doesn't give me a 1. But I also noticed that the -12, to get a -12, one of these has got to be negative. So to get a -12, I need a negative, but I also have to get this +1. So that's indicating that I need a -3 and a 4 for that to work. -3 times 4 does give me my -12, and -3 plus 4 does give me my 1, so that checks out. So this is going to be x minus 3, x plus 4 is equal to 0. So if I find my zeros, all I got to do is set each one of these factors equal to 0. What makes that 0 would be 3. 3 minus 3 is 0. And I can set this factor equal to 0. X plus 4 is equal to 0. And when I solve for x, my 0 is -4. Or again, my x-intercept is -4. So when I graph these, the -4 has got to be on the left, and the 3 has got to be on the right. Notice that behavior of the parabola, since this is the coefficient of a is a +1, we know this parabola has to open up. So it's got to cross through this point, and it's got to cross through that x-intercept as well. And I don't have to really find the vertex at this point, just kind of gets a little bit of the behavior of the graph. Okay, and you also could use your graphing calculator to kind of verify that if you want. So notice how, again, this time though, we're looking for less than 0, which means we're looking for negative. So negative, it's where the graph is below the number line. So notice that between -4 and 3, it's negative. Notice how we talked about multiplicities as well. You know, when we have these zeros, since 3 has a multiplicity of 1 and 4 has a multiplicity of 1, that does indicate that this graph should be crossing over these zeros. So I notice that when you do cross over, there's this sign change. So if you're above, it's positive. When you cross over, it's got to be negative. And then when you cross over again, the sign changes again. So remember, when you cross over the x-axis or this number line, the signs always change. So I'm kind of seeing my solution is between -4 and 3. Now, again, if you're not positive about trusting this, you can always verify this by picking a number left of -4, which would be, say, like a -5. So if I want to verify this, does -5 actually give me a positive answer? So -5 minus 3 times -5 plus 4, well, that's going to be a -8 times a -1. Well, that does give me a +8. So yeah, that's confirming it. That's a positive area. A number between -4 and 3, again, the easiest number to pick for me would be the number 0. So if I test that fact, I'm supposed to get a negative. 0 minus 3 and 0 plus 4. And I do get a -3 times this 4, which is actually a -12. So that's kind of verifying my behavior of my graph as well. And if I wanted to verify something to the right of 3, I could pick 4 there. So it's going to be like 4 minus 3 and 4 plus 4. That's going to be 1 times 8, which would be 8. That would be positive. So again, I'm seeing this again, these alternating of signs as well. So a lot of stuff that we're talking about kind of falls into play here. So our answer is going to be then where it's negative, which would be between -4 and 3. And again, since it's a less than symbol, we do know that these are actually open bounded. It's a less than symbol. We do not include those endpoints. So the solution would be then the interval -4 to 3 would be my interval. So if I want to solve x squared is less than or equal to 36, again, I can set this to 0 to start with. X squared minus 36 is less than or equal to 0. Now to find the zeros, we just set the x squared minus 36 equal to 0. It is solved a couple ways. Since it's just the x squared term, you could just isolate the x squared on one side and go x squared equals this 36. Take the square root of each side, and you would get the plus or minus the square root of 36, which is going to be actually equals plus or minus 6. You also could use factoring on that because it is a difference of squares. So, or you could have said x squared minus 36 is equal to 0. And you could have said, hey, x minus 6 times x plus 6 would be the factorization because 6 squared is 36, and it is a difference of squares. So this would have to turn into a 6, and this would have to turn into a -6 as far as the zeros go. So when I graph this on my number lines, so the -6 would be over here, and the 6 would be over here. And notice that the behavior of the quadratic, since a is positive, it's a positive 1 out here, we know this parabola opens up again. So since it opens up, we have this behavior here going on. Now, since I'm looking for less than or equal to 0, less than or equal to 0 means I have to include the endpoints here. And less than means I'm looking for negativity. So this also indicates that we're looking for a negative value here. So notice how if it's above the number line, this is a positive region. If it's below the number line, it's a negative region. If it's above the number line, that's a positive region. So I want it to be between -6 and 6 as my interval. So -6 and 6 would be my solution. Now keep that in mind though, I should be including those endpoints. So let me back up there and try that again, because since I'm including the endpoints, I should be using brackets, not parentheses. So that's the thing you have to watch out for, is those little details. That's what always gets me as well. So I should have actually brackets there. So if I look at this next inequality, again, it's quadratic. So again, we have to set to 0. Well, it already is. So all I got to do is go 3x squared plus 4x plus 1 is equal to 0. Now to factor this, it does have a coefficient in front of the x squared, which makes it harder, but there's only one possibility for 3x and x. And there's really only one possibility for 1. 1 times 1 is the only way to get 1. So I have to have a 1 here and a 1 here. The catch is the outer and inner terms must give you this 4x. So 3x times 1 is 3x. 1 times x is 1x. And notice how that does give me my 4x. So the factorization does check out. So now we have to set each one of these factors equal to 0. And this one looks a little more complicated. So I'm going to go ahead and write down 3x plus 1 equals 0. X plus 1 equals 0. That one's not as big of a deal. Here I have to do a couple of steps. So I have to move the 1 over first. So that's going to be 3x equals this -1, since we subtracted 1 on both sides. And then to get x by itself, we got to make that coefficient a 1. So if we divide each side by 3, we get x equals this -1/3. And over here, we get x equals a -1. So -1 is actually further left than -1/3. So -1 would be here, and -1/3 would be here. Now, since this is a greater than symbol, I know these are open bounded. And greater than 0 means I'm looking for a positive value. So we also pick up on, as far as quadratic behavior, since this is a 3 out in front, my parabola is going to be opening up. So it's got to cross through here, turn somewhere down there's going to be that vertex, and it's going to go back up. So where it's positive would be left of -1. It's going to be negative between -1 and -1/3. And again, it's going to be positive above the -1/3. Notice again how we talked about multiplicities. 3x plus 1 has a multiplicity of 1. So that means that this -1/3 has a multiplicity of 1. So that means it should cross over the x-axis, and there's a sign change. And we do see that it was negative and it went positive. There's that sign change we're talking about. -1 is also has a multiplicity of 1. So that's how the graph does cross over and make a sign change. So again, we were looking for where it was positive. So again, remember, negative infinity is over on the far left. If infinity is on the far right. And when we do interval notation, you go from left to right. So I should have -1 to, I'm sorry, negative infinity to -1. And the -1 would not be included in the solution in union with. And then we have the other positive interval would be from -1/3 to infinity. And again, we do not include the -1/3. So -1/3 to infinity would be my two intervals for that inequality. X squared plus 11x minus or less than or equal to -10. So this we actually have to set to 0. So I have this x squared plus 11x plus 10 is less than or equal to 0, since I have to add 10 to both sides to get the inequality on one side and 0 on the other. So again, we want to find the zeros, so we can set x squared plus 11x plus 10 equal to 0. Again, this is not that hard to factor, so I really don't need any graphing tools to do that, because remember, x-intercepts are zeros or to these problems. So I could do, again, since it's x squared on front, we just have x times x. And again, the factors of 10, there are not many factors of 10 again, so this is pretty straightforward, hopefully. So we have just 1 and a 10 and a 2 and a 5. That's about all you can use. But the thing is, I have to add up to get this 11. I don't know why I put this XY up over there. Sorry about that. We've been doing XY charts for so long. I forgot that this is just a factor table. So that just means we want a 10 up here. So the factors of 10 that give me the 11 would be the 1 and the 10. So 1 times 10 does give me 10, and 1 plus 10 gives me 11. So yeah, we have plus 1 plus 10. That's got to be equal to 0. We set each factor equal to 0. So that means that this has got to turn into a -1. And this has got to turn into a -10 to make those 0, because -1 plus 1 is 0. And 0 times anything does give me 0. And that's what we have to get is 0. So over here, we need to plot our two zeros. Again, -10 is further left than -1. So I'd have that. Again, the quadratic is a positive x squared. So this again tells me that the parabola does open up. So it does come across here again, just like they all been doing so far. We haven't had any parabolas opening down. That would change things. So again, if I go back to the inequality symbol, notice how it's less than or equal to. So that means we do include these zeros in our solution. And less than means I'm actually looking for negativity. So where it's negative, it would be between -10 and -1. That's where it drops below the x-axis, if you will. So our interval would be then just -10, but again, they're included, so we do need to put brackets there. Try that again. Okay. Where do we go? Get back where we were. There we go. It took off on me. So we do need to use brackets. So I have a bracket, -10 to -1, close bracket. So any number between -10 and -1 should satisfy this inequality. It should make the statement true. So now let's look at linear inequalities with a degree 3. Like I said, the previous strategy can be applied, but when it comes to zeros and the behavior, remember, as we were talking about, if a 0 has a multiplicity of 1, the graph crosses and there will be a sign change. If the 0 has a multiplicity of 2, the graph touches and there's not a sign change. So pay attention to the inequality symbol to determine if the 0 is included or not included in the interval. So notice how if we try to solve this inequality here, it's actually a third degree. So third degree, again, we're going to try to do factoring to start with. So I have this x cubed plus this 4x squared is equal to 0. Notice how there is a GCF of an x squared. So I have an x squared times x plus 4 is equal to 0. So it is factorable. So we set each factor equal to 0. So we have x equals 0, and we have x plus 4 equal to 0. Well, x equals 0 is already solved. X equals -4 would be this one. So again, I would have two zeros here, a -4 and a 0. As far as multiplicities go, notice how the x is raised to a power of 2. So this has a multiplicity of 2, which means that's a touch. That means there's not a sign change. X plus 4 notice that has a degree of 1. So this has a multiplicity of 1. So that means it should cross over. So if we're looking at this, again, since the A out here is a 1, this means the behavior of a third degree, remember a third degree function, it actually finishes up over here on end behavior and finishes down over here. Okay. So if you recall that, our behavior is up and down. If you're not sure about that, then you can always test the intervals. So the graph actually starts down here. When it comes to the -4, it actually has to cross. It has to turn back around. But when it comes to the x-intercept or 0, this 0 as a 0, if you will, it touches and turns back around. So the graph would kind of take on this look. So again, notice how I have less than or equal to. So the -4 and the 0 are going to be included in my interval. Less than means I'm looking for negative. So where it's less than would be over here. Notice how this is above, that's positive. And this is also above, this is positive. So this is a little bit tricky in writing the answer though, because we can equal 0 as well. So there's two things we have to pick up on. So as far as the interval goes, again, remember this is -infinity to infinity. So we do have -infinity to -4. We do include the -4, but what we also have to have is this 0 is actually a solution as well, because notice how it's a solid dot. That means it's part of the answer. So we also have just that one spot there. So we have an interval and just a single number as my solution. So 0 is an answer and an interval is my answer. Now, if you're unsure of behavior, you always can test points in each interval. So if I test the point left to -4, that would be a -5. So if I put a -5 into my factored form over here, so if I have this x squared times this x plus 4, if I'm using that and seeing what it gives me here, if I put a -5 in, notice that's going to give me a 25 here, and that's going to give me a -1, and that is going to be a negative value. So that kind of verifies that. So once you verify one area, remember, that tells you where it starts. And since it starts down low, we can use multiplicity, the multiplicity again to remember what it does after that. So if it starts down low, it's got to cross at the -4, it's got to turn back around, and 0 is a touch, and it has to come back up. So all you got to really do is test one interval somewhere and follow the behavior of the multiplicities to understand what the graph does. So that kind of helps us out a little bit as well as we move forward. So if I look at this example here, we have x cubed is greater than or equal to 5x squared. Again, to set this to 0, we move the 5x squared over. So I have x cubed minus 5x squared is greater than or equal to 0. So again, this strategy is to set this equal to 0 to find the zeros. So if I find the zeros, I have a GCF of x squared comes out again. So x minus 5 would be left over. We set each factor equal to 0. So x equals 0, x equals x minus 5 equals 0. So x equals 0 is already solved. We have x equals 5 here. Again, something to pick up on to a degree 3, since a is positive, we know it's going to finish down and finish up. So from there, my zeros are 0 and 5, but notice that zeros actually has a multiplicity of 2. So that's actually going to have a touch at that spot. X minus 5, that has a multiplicity of 1, so that's going to be a cross. It's going to cross over. There is going to be a sign change. So touch means no sign change, and cross means sign change. So again, if I graph my zeros here, 0 would be on the left, 5 would be on the right. So 0 is the smaller of the two. So my graph is going to come up from here. Notice how it's going to touch at 0 and turn back around, but then it's got to come back up and cross over at 5. So that's going to be kind of my behavior. So from there, we have to pick up on, since this is greater than or equal to, these values are going to be part of my answer. That's going to be closed. And greater than means we're looking for it where it's positive. So notice that if it's below, that's negative. It's still negative here. But notice how once you go right of 5, it's positive. So what I see is, again, there's -infinity way over here, and there's infinity over here. But notice how, as far as the solutions goes, it's 5 or greater. So in other words, we have 5 as our left bound to infinity. And also we just have 0 as a solution as well, since it's a closed point. That means it's part of the answer. So we would have that going on. So that would be, the answer would be an interval and a point, or a 0, if you will. So if I want to solve this inequality, notice how it's already set to 0. So again, we're going to factor. What I can pull out is a 2 and an x. So let's set this equal to 0 again. 2x cubed minus 32x. Kind of got ahead of myself there. So I can pull out a 2 and an x. So if I pull out a 2 and an x, that's going to just leave me an x squared. If I pull a 2 out of this 32, 32 divided by 2 would actually be the 16. So it's going to be a minus 16. And the x came out. So I'm not done factoring because x squared minus 16 is actually factorable. So I have 2x times then, and since x squared minus 16 is a difference of squares, we can set that as x minus 4 times x plus 4 and get that. So we set each factor equal to 0. So we have 2x is equal to 0. So x would equal 0. Null side is a multiplicity of 1. So that's gonna cross. X minus 4 is equal to 0. X equals 4. Null side again, that has a multiplicity of 1. So that's gonna cross. X plus 4 is equal to 0. X equals negative 4. And since that has a multiplicity of 1, that's also going to be a cross. Notice how, again, this is an x to the third. And also how the coefficient out front's a positive. So the behavior should be down and up. So now as far as my zeros go, the furthest left is actually the negative 4. 0's in the middle and 4 is on the right. So you may have to kind of sit back and look at that. Yeah, they're in the right order there. So then notice how it's less than. Less than means we did not include these. This is going to be an open bound, an open bound, and an open bound. They're not going to be included in the solution. So notice how every one of these zeros, it crosses. So this graph is going to come up, crossover, sign change, crossover, sign change, crossover, sign change. So I have that as my graph. Notice how less than 0 means we're looking for negativity. So notice how it's below the graph here. It's above the graph here, that's positive. It's below the graph here, and it's above the graph here. So I'm looking for negativity. So it's going to be, again, from negative infinity to infinity is going to be over here. So negative infinity to negative 4 is going to be part of my answer because that's where it's negative. And then between 0 and 4 would also, so in union with 0 to 4. And none of those endpoints are going to be included in these are going to be open intervals here. So 0 to 4 would also be where it's negative. So that would be your two intervals. So in this case, you know, it's going to be two full intervals in your solution. So next thing we have is what's called solving rational inequalities. So again, we want to identify the zeros of the numerator. We also want to identify the domain restriction, the denominator. The domain restriction will always be open and will not be part of the solution. So keep that in mind. The denominator will never be part of the solution since it's going to be a domain restriction. So what we want to do is we want to place these values on the number line. And then what we want to do, we want to just test each one of these intervals. And the inequality symbol will need to be positive or negative in that situation. So depending on what the inequality symbol is. So on this one, we didn't really get into a whole lot of behavior with these a whole lot. So I'm not going to get into the graphing much. It's just, we're just going to kind of do the old reliable, just test the intervals. So as we say, when you have a rational function, you're going to set the numerator equal to 0, x minus 2. And we say x equals 2 there. That's going to be a 0. And we set x plus 9 equal to 0. And that's going to equals x equals negative 9. So remember, that's going to be a domain restriction. So we're going to exclude the negative 9. So it's always going to be an open circle there. So as we look at this, notice how it says less than 0. So that means I'm looking for a negative value as well. So when we do this, we have two zeros, or I'm sorry, two spots on the number line, a 2, which actually would be a 0, but the negative 9 is actually a domain restriction. And since it's less than 0, we go ahead and exclude the 2 as well. The negative 9 is already excluded. So notice how this breaks the graph into 3 intervals. So to do this, what we need to do is just test each interval. So I'm going to test something left of 2. So that's going to be, say, a 0. And I'm not going to do all the math out. I'm just going to pay attention to the law of signs when it comes to dividing positive negative numbers. So when I put a 0 in, I get 0 minus 2 on the top, and I get 0 plus 9 on the bottom. So that's going to be a negative 2 over a 9. Notice that that's a negative value. So that means that over here, it's going to be negative. Pick a number between 2 and negative 9. 3 would be between there. So if I test 3, I have 3 minus 2 over 3 plus 9. That's going to be 1 over 9. Well, that's going to be a positive answer. So I know between 2 and negative 9, it's positive. If I pick a number left of negative 9, notice how I just did that wrong. I'll have to do that again. Didn't get my order in the right spot, did I? So let's back up here and gotta watch that. Negative numbers are left of positive numbers, so not so good. Okay, scratch that. Make sure you put your zeros on your number line correctly. So negative 9 is actually to the left, and a 2 is to the right. Y'all probably caught that. We're telling me to stop about 30 seconds ago. So let's do this again, where I have to pick a number left of negative 9. Well, that would be like a negative 10. Again, we're not going to do the whole math. We're just going to look at whether the answer is positive or negative. So I'm going to have a negative 10 minus 2 over negative 10 plus 9. So I'm going to have a negative 12 over a negative 1. That's going to be a positive answer. A negative divided by negative is a positive. So left of negative 9 is going to be a positive. A number between 2 and negative 9 would be 0. So let's test 0. 0 minus 2 over 0 plus 9. That's going to be negative 2/9. That's going to be a negative value between there. And to the right of 2 would be 3. So 3 minus 2 over 3 plus 9. That's going to be 1 over 12. And that's going to be also a positive answer. Now remember, the negative 9 is excluded automatically because it's a domain restriction. The 2 is excluded because I can't equal 0. So that has to be an open bound there as well. And I'm looking for negativity. So what it looks like, it's negative between negative 9 and 2. So my solution to this problem should be between negative 9 and 2. And we do not include either one of those intervals in our answer. So that's how we would solve a rational inequality. So if I have this problem right here, again, we have x minus 4 over x minus 7. So to find the 0, I'd be setting the numerator equal to 0. So x minus 4 equal to 0. X equals 4, that would be called a 0. That's what makes the function 0. So if I set x minus 7 equal to 0, I get x equals 7, and that's going to be a domain restriction. So that's got to be excluded. So that's not going to be part of our answer. Notice we have a greater than or equal to. So the 4 is going to be part of the answer. The 7 will not be. The greater than means we are looking for a positive value. So in testing my intervals, left of 4 again would be this 0 over here. So if I put 0 in, we have 0 minus 4 over 0 minus 7. A negative 4 over negative 7, well, that would be a positive answer. So left to negative 4, we're getting a positive answer. Between 4 and 7, 5 is there, so I'll test 5. 5 minus 4 over 5 minus 7. We get 1 over negative 2. That's going to be negative. So between here and here is negative. And then if I choose something to the right of 7, that would be like an 8. So if I choose 8, that's going to be 8 minus 4 over 8 minus 7. That's going to be 4 over 1. So that's going to be a positive answer. So in our solution, we're looking where it's equal and positive. So notice how this negative infinity to 4 is going to be part of the answer. And we have infinity over here on the right-hand side. So where it's positive, it will be between negative infinity and 4, but 4 would be included in union with 7 to infinity, but 7 would not be included. So 7 to infinity would be the other solution to this inequality. So let's see what else we got here. Got a couple more. All right. So we'll finish up these last two examples here. So to do this one though, notice how we're not in luck here because it's not set to 0. So we got a little bit of math to do here. So we have to move this 1 over to the other side. So we have x plus 6 over x minus 3 minus 1 is greater than or equal to 0. Now, to make a rational function, we need to have all this under one denominator. So since x minus 3 is the only denominator, what I can do is rename the 1 so it has the same denominator. So I can write this as x plus 6 over x minus 3, and I can rename 1 as x minus 3 over x minus 3. Notice the numerator, since there's a subtraction sign here, it's kind of important to keep the parentheses in the top. So when you put this together now, because remember, if you have like denominators, you just put the numerators together. So this is going to be x plus 6. And when you put the top together, the subtraction sign's got to go through. That's going to be a negative x plus 3 over x minus 3, since we keep the same denominator there. So in this problem here, it looks like the x's are going to cancel out, and we're going to get 9 over x minus 3. So it looks like in this one, there's only one thing that we have, and that is a domain restriction. So x cannot equal 3. So that's going to be what we put on our number line is the 3. Also, we got to keep in mind that this was greater than or equal to 0 as well. So this is going to be greater than or equal to 0. So we're looking for what makes it 0 and what makes it positive. Notice that you really can't make it 0 because the numerator is a constant, so that can't happen. So it looks like we just have this 1 0 to put up here, and that's the 3. So if we test left of 3 and right of 3, that should take us to the end of this problem. So we're looking for where it's positive. So if I put a 3 into my problem, pick something left of 3 would be, again, 0 would be a good choice. If I put 0 in, that's going to be 9 over 0 minus 3. That's going to be 9 over negative 3. That's going to be a negative. So let's pick something right of 3. Right of 3 would be maybe like a 4. So this is going to be negative over here. Right of 3 would be a 4. So I have 9 over 4 minus 3. That's going to be 9 over 1. That's going to be positive. So it looks like right of 3, we end up with a positive value. So it looks like based on the strategy, we should have an answer that is to the right of 3. And again, notice that we can't include 3 in this problem because it's a domain restriction. So our answer ends up being then open bound at 3 to infinity would be our solution. So let's look at number 4. X minus 2 over x plus 7 is less than 1. Again, since we have a 1 here, we can't just go with it. We have to set this to 0. So I have x minus 2 over x plus 7 minus 1 is less than 0. Again, we need to make this a rational function, so I need to get a common denominator. Since x plus 7 is the only denominator, all I got to do is really just rename the 1. So x minus 2 over x plus 7, and just make the 1 x plus 7 over x plus 7. Again, since there's subtraction, I got to remember that the subtraction sign has to go through both pieces there. Okay, so this becomes then x minus 2 minus x minus 7 over x plus 7. So this gives us then, again, our new function is going to be negative 9 over x plus 7. And that's going to be less than 0. So notice how again, we cannot equal 0 here, but the less than means we're looking for negativity. So notice that the only thing we have to deal with is a domain restriction. So in our problem, x plus 7 equals 0, x equals -7. That's going to be our domain restriction. That's the only 0 that we really have, but it's just actually a domain restriction that we want to put on there. So on our graph, we're going to put this -7 here, and we're just going to test the interval. So again, if I choose left of -7, that'd be like a -8. So again, I had a -9 over x plus 7, I believe, was what we had down here. So if I put a -8 in, that's going to give me a -9 over a -8 plus 7. That's going to be a -9 over a -1. Well, that's going to be a positive answer. So over here is going to be positive. If I pick a number right at -7, well, 0 is way over here. So I like to choose 0 when possible. So I have a -9 over 0 plus 7. That's going to give me a -9 over 7, which is going to be a negative answer. So it's going to be negative to the right of -7. So it looks like our less than symbol means we're looking for negativity. So it looks like, again, we have -infinity over here to infinity over here, but we also have -7 is involved here. And where it's negative at is from -7 to infinity. So I use -7, but I don't include it to infinity. And that should be the solution to our problem. So hopefully that will help you with your homework. That concludes our lesson.